So last time we were actually, talking about these collisional processes, right? So there are different kinds of collisions in the interstellar medium. You can have collisions between electrons and ions. Uh, you can have a collision between electron and a neutral, and the electron uh, uh, can ionize the neutral, for example. You can have collisions between an ion, say OH minus, and a neutral. You can have collisions between electrons and molecules. You can have collisions between two neutrals, like two H2. You can have collisions between dust particles and molecules. So the collisional processes are one of the most important process, the microphysical processes in the interstellar medium. Okay, so it's a good idea to have some feel for it. So last time we were actually talking about these Coulomb collisions. So Coulomb collisions are between two ionized species because they interact with this long range 1 minus 1 by r potential. Uh, and a generic feature of these is that uh, these are long range forces. So the cross section, there is a logarithmic dependence of uh, the total collision rate or the cross section on these cutoffs of these integrals, right? You do this integral over all impact parameters, B, and you have to use some B min to B max. We have encountered this even in the gravitational two-body relaxation problem, right? So here the B min is the impact parameter when this approximation of this impact approximation in which the projectile essentially is unperturbed breaks down. Okay. That is when the kinetic energy becomes comparable to the potential energy. If you recall from the gravitational equivalent of this, this V escape by V the whole square, that was the deflection angle, right? That so if your escape velocity from that charge or mass is very high compared to the velocity, V escape has to be very low. Sorry, the other way around. Because if V escape is very high, that means the gravitational potential, the binding potential is very strong. So all these ideas sort of apply. So let's get started. So last time I also mentioned this difference between collisions do several things. Through collisions, particles can transfer momentum, they can transfer energy, and the time scale for transferring momentum and energy are different, right? Because imagine a proton and an electron hitting the proton or getting colliding with the proton. Since electron is such a low mass, uh, has such a low mass compared to the proton, electron can get substantially deflected, right? Just go to the example of a collision between two particles. One of the particles is very small, less massive. The other is more massive. In the collision, what happens is that the less massive particle just reflects its velocity. So momentum exchange has taken place, but no energy exchange has taken place because the V goes to minus V, so the kinetic energy remains the same. So if you have such a situation, then electron can deflect on a short time scale, but it cannot exchange energy with proton on the same time scale. The energy exchange time scale is factor of 2000, the mass ratio of proton to electron times larger. You need that many collisions in order for them to exchange energy. Okay, so last time we actually derived it. It's useful to actually know these qualitatively and mathematically. Okay, so and then So then we also sort of looked at some applications of this Coulomb scattering. And this B max, the integral over the impact parameter, is the Debye length. That's sort of also natural in a plasma. Unlike in a gravitating system where where there is no shielding. Right? If you put a mass here, it's not like negative masses can come and shield your mass from the outside world. So there, B max was the system size. Okay. So let's sort of do a little bit of recap. So we were doing this collisional ionization. So of a loosely, so we were actually considering something like you have a nucleus and you have a electron bound in a high orbit, a large n orbit, far away from the nucleus, and then you have an electron which comes from here. It's sort of this is very loosely bound. So you can actually think of this collision as between this electron and this electron, rather than between this electron and this charge here. Okay, and if this electron has sufficiently high energy, what you can have is you can leave behind this proton or this nucleus, and you can have two electrons which are sort of free, right? So this is collisional excitation of a high n. Here n is this energy level, right? Just like hydrogen atom, you have n equal to 1 to n equal to infinity. Okay. So in order for this electron to be able to ionize this weakly bound atom, what you need is half me v squared has to be greater than the ionization potential. This and so we actually also had written this, if you recall, the delta p perp, the momentum in the perpendicular. So you remember you have a target at rest and you have a projectile, and in single interaction, the target receives a momentum in the perpendicular direction. Okay. So this delta p perp was actually f perp times the interaction time. So we did that the integral, if you recall, f perp dt. Why did it happen? Okay, so this is f dt by m. No, this is momentum. So this is just a dp dt is f. So right. So this f perp was z1, z2. So e squared by b, and the tau by b squared. Right. So if you recall, you have this geometry. This is b. The interaction happens essentially for a time which is 2b by v. Right. So this is a nice way of doing, just remembering. This is the force at the impact parameter location, and this is the time for collision. So this gives you your delta p perp, and this is proportional to 1 by v. The faster the projectile is, the less the less momentum it gives to this this guy here. Okay. Yeah, projectile can be an electron hitting a proton. You can have a proton hitting an electron. You can consider all these combinations. Yes, yes. So you can have two ions with charge Z1 and Z2. This is a general expression. Okay, but here we'll apply, like, we'll use Z1 equal to 1. because this is an electron. And it's essentially the same idea applies for like charges and unlike charges, because the deflection is in random directions. Right? You can have a charge here which deflects in this direction, and you can have a charge here which deflects in the other direction. So irrespective of the charge of the projectile, you have a random walk in the perpendicular direction. Right. Yes. Yeah. I mean, yeah. So in this case, Z1, this has V1, and Z1 is equal to 1, and you can have some Z2, something like this. Okay. So this is the amount of momentum. So as I mentioned, you can actually think of this as a collision between these two electrons. Okay. Yes, of course. No, then we are integrating over all B's. No, eventually this is for a given B, and then you sort of integrate over all B's. Right? The whole procedure is this, and that integration over all B's gives you this log B max by B min. So right, so for a given velocity, your right, so delta P perp squared by twice ME should be greater than the ionization potential, right? So this delta P perp squared by twice ME is the momentum this electron will receive in this collision, right? Because delta P perp is the momentum in the transverse direction, and the energy corresponding to that is this. Okay. So, but we know the expression for delta P perp, which is given here. So Z1, Z2, E squared by B has to be, and the square of this, so this is delta P perp squared by twice ME, has to be greater than I for ionization to happen. Right? For a given V, we know what B should be. B should be smaller than this B max, which I'm going to write B max is equal to, right? When you equate these two, you get B max. If B is less than B max, then this is larger than the ionization potential. Okay, so B max is equal to square root of 2 ZP E squared by MEI times V. So this is just obtained by this equality. Now, the sigma for a given velocity for ionization is nothing but, these are twiddle, these are only approximate calculations, mind you, but the scalings with respect to temperature and so on will hold, but the coefficients will not be right. Okay, so there are tables of these things which you can look up if you're interested in quantitative expressions. So this is pi times B max squared, and that's just so 2 pi ZP squared e to the 4 by MEI V squared. So this is the, you recall there are two sort of important quantities in these type of calculations. One is this cross section as a function of energy or as a function of velocity, right? So the question is, if you have a target and if you have a projectile, and if you shoot the projectile with velocity v, what is the probability of it interacting with the target, right? For a given velocity. And then there is this concept of rate, right? There is this rate coefficient, which is this sigma times v, which you integrate over all velocities. right? So this is a centimeter cube per second. Right? This is centimeter squared. This is centimeter per second. So centimeter cube per second, because it's an it's a two-body process. So n1, n2 times this will give you rate per unit volume, if you recall. So this is averaged, integrated over all velocities for a given temperature. What will be the rate of this reaction? So two quantities, sigma v, and then this average over sigma, or average over velocities of sigma times v, which gives you rate coefficient. So what do we? Sigma is cross section, scattering cross, or interaction cross section. It need not just be scattering. You can have any interaction between the projectile and the target. It need not just be like reflect. You can have chemical. You can have cross sections for chemical reactions, right? If you say shoot electron beam on protons, what is the cross section for them forming neutral hydrogen, right? So you can have a general, and this is a very, very wide concept, like in particle physics experiments and so on. This is what they do all the time, right? That you have this, you're shooting, so you're colliding protons with protons, hadrons with hadrons, and you're just seeing what are the distribution of different particles produced at different angles at different energies. And this sigma can also depend on angle, right? For example, in Thomson scattering, the scattering is, it happens perpendicular. So if you have a light with the polarization in this direction, so the target oscillates in this direction and it radiates in the perpendicular direction. So this is a very, very general concept. So you should have a good feel for it. Okay, so this is sigma b. This is the rate coefficient, and this would just be integral from v min to infinity, right? Not all velocities will ionize your atom. There is a minimum velocity, which is nothing but twice I by me. Right? So the kinetic energy of the electron has to be at least, or the velocity has to be at least this much in order for it to ionize. And then you have your usual sigma v times v fv dv. And this fv now can be your Boltzmann, Maxwell-Boltzmann velocity distribution. So if you do this, okay, so yeah, it's a good idea to know these expressions. Exactly, it's not that hard, right? You've already, so fv is equal to 4 pi e to the minus half mu v squared by kt, 1 by 2 pi kt, 3 by 2. I think this is correct. So if you integrate it over dv, you should get 1. So if you plug in all this, and if you do this in mu kt, yes. Yeah, I think this is what it is, because it's like 2 pi v thermal squared. Okay, right. So so we know this fv, we know this sigma v, we know the limits of this integral. Let's see. I will actually not do the integral. You'll actually encounter this 2 pi kt all the time now, in this class and in the next class. Okay, this is just thermal velocity cube, essentially, right? V thermal is kt by mu, right? So So let's look at it. I will not do this integral because this 4 pi's, 2 pi's to the 3/2, all these, I'm not going to do it. But let me just show you what you expect to get. So you have a v squared there. So it's sort of the integral will be of this form. So you'll have say x squared. So this x is from this v. So actually no, yeah. So this x is due to this v. This x squared is due to this v squared. Fv is e to the minus alpha x squared dx, right? This and then you'll have a prefactor. This is the kind of integral that you have. This is like a Gaussian, and this is a Gaussian, and then you have this. These integrals are very easy to do, right? So if you do this integral and retain all the prefactors, what you get for this is right. So here is the okay. So there is also the sigma v, which has 1 over v squared, which will be 1 over x squared. In fact, this is even easier, right? So you have x e to the minus alpha x squared. In fact, this is just e to the minus t squared dt times t, sum a to infinity, and that's just a trivial integral which you can do, right? This is just e to the minus s ds by 2, and then a to infinity. It's just e to the minus a by 2, something like this. So if you do that, what you will get is the following. This is zp squared. This is just this zp squared. Zp squared 8 pi me, and mu. Mu is the reduced mass, of course. Okay, so for collision between electron and electron, mu is just me by 2. For electron and proton, mu is just me. So me kBt 1 by 2. So this is also easy to see, right? Dimensionally, FV dV is, FV dV, if you integrate, you should get 1. It is dimensionless. FV dV does not have a dimension. Then sigma goes like 1 over v squared. There is a v here. So the quantity that you'll get in the end is like 1 over v dimensionally. And the only velocity in town is square root of kt by m. So you will have a square root of kt by m in the denominator where you have. So this is t to the minus 1/2. What? Of the sigma times v? Yeah, but FV dV is dimensionless. Yeah, so no, I mean the dependence on velocity. I don't mean the dimensions in that way. So there is only like a 1 by v, and v we will de-dimensionalize with v thermal. So that's why in the end what you have is 1 by square root of t here. Okay. E to the 4 by I e to the minus I by kBt. Sometimes I'll write kb and sometimes I'll just write k. So just be careful. Rate coefficient is right. So if you remember, so if you have a plus b going to c, okay, and it's a collision between a and b which creates c. So the rate coefficient means that the rate of the forward reaction, the rate at which c forms, is equal to sigma v times na and b. This is what rate coefficient represents, right? It's a two-body process. It will be proportional to na and b. This is independent of density. So the rate coefficient just determines how efficiently these two particles interact or collide or whatever, react. Okay, so this is the expression. So this is the sigma v for collisional ionization of a high, right. So this is for collisional ionization. Then if we apply it to, say, the electron is in a high n state, so n is much bigger than 1, right? And we know we know for a single electron system, like a hydrogen atom, we know that ionization potential is equal to I h by n squared, right? 1 by n squared is the ionization potential from a level n. Let's just take it to be, okay, yeah. There is also z squared, but let's just take it to be a hydrogen. So for hydrogen, then so, and if we say n equal to 100, right, or n equal, very high level. Actually, it turns out that even these very high energy levels are important in the ISM. Naively you would think, why should we bother about an electron which is in n equal to 100 state of a neutral hydrogen atom, but they are important. So in that case, this is 13.6 eV. So this will be really small. And if you have if you consider a temperature of 10 to the 4 Kelvin, that's like a typical warm interstellar, warm neutral medium, right? If you remember last time I talked about the phases of the interstellar medium, 10 to the 4 Kelvin, 5000 Kelvin, that's about the range of temperature at which most of the mass of the ISM is actually. Okay, so in this case, for n of order this much, so I by kT is much less than 1, right? Ionization potential for n equal to 100 is actually much less than the thermal energy. So this exponential is 1. E to the minus that factor will become 1. So sigma V collisional ionization will be, and if Zp is 1, we'll just have 8 pi me kBt half e to the 4 IH. This is the hydrogen ionization potential from the ground state times n squared. So what you see is that if you have an electron in a high n state, and if it undergoes collision with an electron, the probability of it getting ionized is very high. It goes like n squared. So if you have an electron in an n equal to 100 state, and if you have a collision, it is 10 to the 4 times more likely to get ionized compared to the electron which is sitting in the ground state. Okay. So this is one application of, the same ideas, collisions. Okay, let's go further. So last time we talked about this deflection time and the energy transfer time. So I won't cover that again. Now let's talk about, and this is, so when you are in this impact approximation, that is, you have a fast projectile and it essentially goes in an unperturbed trajectory. This is an elastic collision, right? There is no energy loss for the projectile. But you can also have inelastic collision. So inelastic scattering. So this is sort of the picture. So you have a nucleus, and you have these, orbitals, and you have an electron which comes and sort of hits. And this is some upper level U, and there is a bound electron in some upper level U. Okay, electron from infinity comes, hits it. After this interaction, this electron goes from U to L, some lower energy level L, and this electron gains energy, right? Because this releases energy and that can gain energy. That's also inelastic. Or the other way, it's also inelastic. So when does that happen, right? If you have electrons, in order for your electron to cause these transitions, it should have an energy comparable to the binding energy of this electron, right? Otherwise, it is like is it? So, so what it means is that the B, the impact parameter, is of order A naught, right? Where A naught, if you recall, is A naught is Bohr radius. The size of these orbits in atomic theory are of order A naught, and A naught, if you do your Bohr hydrogen atom, is just h cross squared by me e squared. CGS units, no 4 pi epsilon naught here. Okay, so this is your Bohr radius. And so we are interested in this. Right? So sigma v, the rate of this, the rate coefficient for this interaction, for this collisional interaction to transition from an upper state to lower state, is given by this. And so first, let me actually give you a heuristic. So when the electrons do not penetrate too much inside, if the impact parameter is too high, they are essentially, not causing these transitions in the atom. They're elastically getting scattered. But if you sort of come closer and closer and become of order the atomic size, then right, so this cross section, right, is just basically pi b squared, where you want to use right. This is this distance of closest approach. But here we want B to be of order of some few W times A naught. Right? So it comes within a few A naught so that it can do this thing. So in this case, the effective cross section is no longer this, right? It is like A naught. Okay. So how do we write it? So in this limit, it actually becomes, you can actually write it as de Broglie wavelength squared times V. I mean, so this cross section actually becomes like de Broglie wavelength. Okay, and so let me actually write down the expression and then I'll explain. So this is h by 2 pi me 3 by 2 k 1 by k t 1 by 2 times omega ul, which is a function of weak function. So this is a weak dependence on t, and gu. Let me just write it down and then sort of motivate it. Right. So what is de Broglie wavelength? De Broglie wavelength is h by mv, right? If you're, h is Planck's constant, v is the thermal velocity or the velocity of the particle, and v is of order kt by me, right? So there is a squared here. Oops. So h by m squared v squared, right? So de Broglie wavelength squared is h So h squared, m squared, v squared. This is de Broglie wavelength squared times v. So, and that's just, this is sort of m times kt by m square root, right? Which is nothing but this. So m squared. Sorry, yeah, there is m to the 3 by 2. Okay. Right. Now this form is used all the time for this inelastic scattering. So you have an electron, you have a neutral atom in some upper state, and it transitions to a lower state. Okay, and this is how it is expected to scale with temperature. So higher the temperature, lower is the rate. And this parameter is called, this is dimensionless. This is called collision strength. This G is the degeneracy factor of this upper state U. So, right, for example, in hydrogen atom, the degeneracy of an electron in a state n is 2n squared, right? There are 2n squared orbitals. Right? The 2 comes from the spin degeneracy. N squared comes from the fact that you can have L's, which goes from 0 to n minus 1. And you can have M's, which goes for each L minus L to plus L. So it's all your chemistry, all the quantum mechanics when you did sort of periodic table. It's sort of that, and of course the wave functions and so on. Okay, so this is sort of the form that's usually written all the time. So you will find tables of omega UL, right? This is just the quantum degeneracy. Okay, there is another way of sort of getting the same thing. Let's look at that another way. So suppose you want to get this rate coefficient. This we write as pi w squared a naught squared, right? So this is pi times some length squared. So I'm saying the impact parameter is of order this much. Okay, so let's consider let's consider a positive charge, here, and an electron here, and this electron comes. If it has an energy which is smaller, there can be quite a bit of focusing, gravitational, or electrostatic focusing. The electron can be pulled in. So so 8 kT by me. Right, so this is 1 by 2. So naively, you would expect this to be cross section, right? So I'm saying that the electron comes at a distance of order WA naught. Okay, but because of this electrostatic interaction, even the farther away electrons, will be deflecting somewhat. Okay, and this actually is just 1 plus ZE squared by WA naught KBT. So let me just write down. So this is this electrostatic focusing factor. So let's see, how do we explain it? So if you have an electron here, and if you have a charge Z here, okay, so we want to write this distance of closest approach. So half me v infinity squared is equal to half me v v max squared. So v max is the velocity at the distance of closest approach, minus z E squared by R min, right? So, and this is like B. The other thing is that angular momentum is conserved. So V infinity times B is equal to R min times V max, right? This is this is the conservation of angular momentum relative to this point. So B times V infinity, the velocity of this electron at infinity, is equal to this R min times the velocity at that point. So there are two equations and two unknowns. So two unknowns are R min and V max. And these are the two equations, energy conservation and momentum, angular momentum conservation. If you put that in, and then you can relate R min and B. So what you find is that B, B is equal to 1 plus ZE squared by R min. Right, so let's see. Right, so V max, the velocity here will be larger because it's an electrostatic attraction. So this velocity becomes larger. So R min will be smaller. So the distance of closest approach will be smaller than the impact parameter. Okay, and the impact parameter will be a factor of this much bigger. So this is the source of this. This is sort of the source of this, that previously in the impact parameter, we just sort of assume that this projectile is undeflected. But here, deflection is very important. In fact, this factor is much bigger than 1. Right, so this is the difference from the previous case. In this case, in this inelastic scattering, this factor is important. So you can actually see that if you just ignore this 1 and you just retain this kt, there is 1 by square root of t in the denominator, like in this expression. Right? This is a heuristic way of doing it, right? Instead of your b, you just put the de Broglie wavelength and you get the expression with the right dependence on temperature. This is a little more formal way of doing it. Yeah. B by R min whole square. Okay, good. I think that's what we need here because it's cross section. So it should be the squares which come here. Yeah, I have not actually worked it out. I just, I just sort of know the idea, but I have not written it in my notes. Okay, good. So that's why it's not just WA naught. The cross section is not just WA naught. Even the particles which are much farther away than A naught will be significantly deflected because of this electrostatic focusing. Right. So this is sort of the V escape squared by 2. Right. The V escape squared by 2. If that is comparable to V infinity, if this and this are comparable, gravitational focusing, or if this is much bigger than this, gravitational force focusing can be very important. Okay. So this was ion electron ion scattering, inelastic scattering. So you in an inelastic scattering, the kinetic energy is not conserved. Okay, so you can also have ion electron, ion neutral. Sorry, not electron. Collisions. So in all these, this sigma v is proportional to 1 by square root of t. Even here you will see this. This is 1 over square root of t. In all these collisional, Coulomb collisional processes, that's true. Okay, now a neutral atom hitting an ion, they don't interact with Coulomb interactions because neutral is neutral, right? What happens is if you have an ion, say Ze, an ion, and if you have a neutral molecule or an atom here, what it does is it polarizes the molecule. So it will induce an excess. So say this is a positive charge. This is your nucleus of the atom. So you'll have a little excess negative electron cloud here and positive electron cloud here. And since the electrons are closer to you, you'll have some attraction. And so this is a positive ion. This is neutral. It gets polarized. It induces negative charges here and excess positive charges here, and there is an attraction. So this is a induced dipole interaction. So let's see. So you have this polarized, this the dipole moment equals alpha n times E. This is polarizability of the molecule, polarizability of the neutral molecule, ZB. This is the electric field due to the ion. And P is dipole moment. That is induced in this neutral atom. Right. This polarizability has a dimension of 1 by length cube, right? Because electrostatic, electric field goes like P by distance cube. For a monopole, electric field goes like 1 over r distance squared. For a dipole, it's 1. So this has a dimension. This is of order actually. Alpha n is of order a naught cube. A naught is this atomic dimension, right? Bohr radius. So physics-wise, these are all extremely hard topics. Because this is what you do using like your time-dependent perturbation theory and all that. But here we are sort of doing semi-classical treatment of these things, and we get more or less correct expressions. Okay, DDR of 1 by r squared gives you 1 by r to the 5. Okay, so this is what you have. So this is the force which goes like 1 over r to the 5. Contrast this with Coulomb force, which goes like 1 over r squared. So this sort of falls off much faster with distance. Okay, and this corresponds to a potential or potential energy, interaction energy between this ion and this atom due to this induced dipole is -1/2 alpha n. Alpha n is this polarizability, z squared E squared by r to the 4. Right. So this is the potential energy. Now, what do you have to do now? So for example, for a -1 by r potential, we had to solve for the orbits, and we use this simple impact approximation and whatnot. You have to do the same exercise here. And we know that these are not like easy, only 1 by r, minus 1 by r, and proportion to r potentials have these closed orbits. And so the orbits here will be extremely complicated. Okay. So, if if you throw a projectile at far distances, of course it gets like this. But you can, if you are coming close, you can even have orbits like this. You can have these crazy looking orbits. So it turns out, again, I'm going to write this as a fact. Okay, well, I'm not gonna derive it. So there is a critical distance B naught. B naught. So for B greater than B naught, you have like you have these kind of orbits, right? You have like passing orbits. But for B less than B naught, right? At small distances, these are very strong interactions. Unlike Coulomb interactions, where even at large distances you have, in fact, the interaction is dominated by large B's in Coulomb. Here, that's not the case. Interaction happens only within B naught, and a very strong interaction happens only within B naught. And what is this B naught? B naught is this impact parameter for which the interaction energy is equal to minus kinetic energy in the center of mass frame by 4. And this is like this is just a thing that's given by looking at these kind of orbits. Okay. And if you do that, so if you equate this to, and ECM is nothing but energy in the center of mass frame. That's nothing but half mu v squared. Okay. If you equate 1/4 of this and this, then we get a value of B naught, and B naught is equal to twice alpha n z squared E squared by E center of mass to 1/4. Right? This 1/4 comes because it's a 1 by r to the 4 potential. So this is the scale in the problem, essentially, right? So effectively what you say is that strong interaction only for B less than B naught. For B greater than B naught, there is no interaction. You can essentially ignore those kind of interactions. But if B is less than B naught, what you can have is these complicated trajectories. And the system that forms here, you can actually think of this for B less than B naught. You can actually think of these trajectories as forming some sort of a complex. It forms an excited complex, some sort of a resonant interaction, you can think of it. And this excited complex will sort of decay for all, it will easily decay to all possible lower energy states. So the reactions are fast if you are able to form this kind of an excited complex. Okay. So these are important for reactions like charge exchange. So charge exchange reactions are something like you have a neutral, you have an ion, they collide, and they form this complex, and then this complex decays into another neutral and another ion. So let me give you an example. So O plus hydrogen gives you O in 3p0 state. These are term symbols used in spectroscopy. So I'm actually not going to explain it right now, but this is oxygen in an excited state, neutral oxygen, but electron is not in the ground state, but in an excited state, plus H plus. So this is a charge exchange reaction, right? You had an oxygen ion and a neutral hydrogen. It gives rise to, after forming this complex, you form a neutral oxygen and a proton. Similarly, you can have something like H2 plus H2. This gives rise to H3 plus hydrogen. This is a chemical exchange. Yeah, here also you have an ion and a neutral, and it sort of gives rise to an excited state which decays into this kind of a thing. All these are exothermic reactions. So in the sense that they are energetically favorable. Once you form this excited complex, it will decay to the ground state. If you're not able to form that excited complex, it's sort of like these reactions, right? You have this reactants and you have these products. Reactants are at higher energy state, but there is a little barrier, right? And if you have done chemical kinetics, this is a very generic thing that happens. The ability to form this complex means that you are able to jump over this barrier and go to this lower energy state. So CH plus H2 gives CH2 plus hydrogen. Again, this is a chemical exchange. So here you form a different chemical ion, whereas here you just exchange charges. This charge exchange is very important in the solar wind. So the wind from the sun, there is a wind of charged particles coming out from the sun, and the solar system is moving into the interstellar medium. Interstellar medium has a lot of neutral stuff. Those neutral ions, those neutral atoms, do not feel the magnetic forces and all those. They just sort of come into the solar wind. And now you have a neutral ISM atom, and you have the solar wind ion. They can charge exchange, and that produces X-rays. So these are actually very important reactions happening across the universe, actually. Okay. So what is the rate coefficient for this? Sigma times V. What is that? So let's see. First, let's look at sigma. What was the value of B naught? Right? Sigma is nothing but pi B naught squared. Right? I mentioned that if B is less than B naught, there is no interaction. For B less than B naught, very strong interaction. So then B naught is given here, and B naught squared. So the sigma is 2 pi ZE alpha n by mu to the 1/2 times 1 by V. Let's see if this is correct. So B naught, so ECM is half mu V squared, right? This is equal to half mu V squared. Mu is ME, or here we'll not take it to be ME because we are thinking about ion and a neutral atom or a neutral molecule. So here it's not a collision between an electron and something. So here we have to retain mu. Okay, so if you plug this in here, you do get, if you squared it, you have 1 by V. Yeah, you can see it, right? 1 by V squared to the 1/4, and you square it, that just becomes 1 by V. So sigma is proportional to 1 by V. So it's very interesting. This reaction rate coefficient is independent of V, because V just gets multiplied. So this is just 2 pi ZE alpha n by mu to the 1/2. Right. So this is the charge exchange reaction coefficient. So here, what we just said is that as long as you're able to form this excited complex, any exothermic reaction will just happen after that. Okay. So have you guys encountered this? You have this A state and a B state. in chemical kinetics. What is it called? This is an activation energy, right? This is called the activation energy, which in this case is provided by this collision. So there is a great analogy with chemical kinetics of this. Yes. Yeah. So this excited complex is that intermediate excited state. In fact, Saha derived his ionization formulae based on advances made in chemistry and treated ionization recombination as a chemical reaction. Okay. Right. So one thing to notice here is that there is no this is independent of temperature, right? Of temperature. The Coulomb interaction coefficients, so sigma V Coulomb, were all proportional to 1 by square root of T, right? So if you go to lower temperatures, right. So at lower temperatures, of course, you also have the things become neutral. Right? They are no longer ionized at lower temperatures. So these are important interactions in cool ISM. So chemistry of cool interstellar medium. And these, since these are independent of temperature, their reaction rates are still reasonably high at low temperatures. Whereas if you have neutral collisions, for example, right? So sigma for molecules is just the molecular size squared, right? So for say neutral in the cool ISM, if you think about neutral reactions, that's just pi times A naught squared. A naught is some size of a molecule. Okay, that's independent of temperature. So that's your cross section, and then sigma times V in this case will be proportional to square root of T, right? V is proportional to square root of T by M. So these reactions become very weak at very low temperatures, whereas these are independent of temperature. So these are very, they happen much more than these neutral reactions. Okay, so try, there are these terms that you should be able to distinguish in your minds, right? Charge interaction, charge neutral interaction, ion neutral interaction. They are all different microscopically. Here we are sort of looking at the microscopic picture, which has sort of implications on macroscopics as well. Okay, so this was ion neutral interaction. And of course, the momentum transfer rate, once this excited complex forms, the incoming ion, is ejected in a random direction. So this is also roughly a pi B naught squared, where B naught is this guy. This, right? I have actually used this sigma V for different purposes. This is sigma V for chemical reactions that I consider here. This is sigma V for momentum transfer. Once you form this excited state, the incoming projectile can be sort of kicked out in any direction, and sort of cross section for that is roughly the same as for the chemical reaction. Okay, so this is ion neutral. What about electron neutral? Sorry, there has to be, my bad. There has to be. It's basically the same as this guy, is what I meant. Right. So pi b naught square is area. Sigma times v is a centimeter cube per second. It's a rate coefficient for two body interaction. So what about electron neutral? So when an electron hits a neutral atom, like say hydrogen atom, or a molecule, in fact, even better. So you have an electron, you have a hydrogen H2 molecule. It can, if it has enough energy, it can excite transitions. What it can excite are things like it depends on energy. So if your energy of the electron is less than 0.04 eV, it does not have enough energy to excite any of the transitions. It cannot do rotational, or see, in quantum mechanics, you need, the ground state has some energy, and there's a gap between the ground state and the next excited state. If the electron does not have that much energy, it cannot excite those transitions, right? In quantum mechanics, energy in the root. So if you have, say, CO molecule, consider CO or HH, what are the degrees of freedom that it has? It can have rotational motion, right? It can rotate. But if your electron has an energy which is less than the n equal to 1 and n equal to 2 rotational energy levels, then this rotational motion cannot get excited. The other possibility in molecule is that vibrations. Vibrational energy levels are even higher than the, it's easy to rotate the molecule than to vibrate, to be able to vibrate it. That's sort of a higher amount of energy. It requires higher energy. And the highest energy is to do these transitions between different orbits, right? The electronic transitions. So if energy is less than 0.044 eV, this corresponds to less than 500 Kelvin. Then, this elastic scattering, there is no energy exchange. It does not excite things or de-excite things. If it is between 0.044 and 0.5 eV, then you can have rotational excitation. If it is, greater than 0.5 but less than 11 eV, then you can have vibrational excitations. I think this is for H2. Okay, and then if you are greater than 11 eV, you can actually have electronic excitations. Okay, so so let's see, the rotational, right? So right, so E rotational classically is, right, J squared by 2I, where I is the moment of inertia, J is the angular momentum. And quantum mechanically, this becomes an operator. And so similarly, the vibrational energy has like H cross omega kind of, where omega is the frequency of this oscillator. If you have this H2 molecule, and it's sort of, if you perturb it a little bit, it will do these oscillations. That's the frequency of that oscillation. Right. So you can actually calculate order of magnitude of these things. Right. So J is like right. So moment of inertia is like MP, A naught squared. This is of order this much. Right? A naught is the Bohr Bohr radius, and MP is the proton mass. So moment of inertia is roughly like that. J is like your angular momentum, so it's like H, NH cross or NH or something. So if you plug this in, you can actually calculate what will be the rough order of your rotational energy levels. Okay, and if you, yeah, it's a good idea to have this intuition. The problem with quantum mechanics is we can do operators and bras and cats and blah blah, but there is a semi-classical way of looking at all this as well. That's actually quite useful in real life applications like this. Okay. So you can actually have, you can have sigma momentum transfer, and you can have sigma v calculate. There are expressions for this. This is a different kind of interaction. Okay, and we will actually not go into it. So this is electron H2, or say electron and helium, and so on. These are it is. And then of course we have neutral that already hinted at, right? Neutral, sigma is equal to pi times R1 plus R2, the whole square. So if you have two molecules, one with size R1 and the other with size R2, and if I throw it here, if they are separated by a distance larger than R1 plus R2, if B is greater than R1 plus R2, there is no interaction essentially. It just passes. So sigma is equal to pi times R1 plus R2 the whole square, where R1 and R2 are the sizes of these molecules. Now, molecules have very complicated interactions between themselves. So if molecules, if molecules are close together, they feel a slight attractive force, like a van der Waals force, this is called. And that's actually a very, in this case, UR for these, it's sort of like induced dipoles. That goes like 1 over R to the 6. Recall this ion induced dipole was 1 over R to the 4 potential. This is 1 over R to the 6, even longer range. And if you put the molecules too close to each other, within a distance less than R1 plus R2, there is a strong repulsion. It's sort of, you can take it as a hard billiard ball. But yeah, so this is it. So this sigma is independent of velocity, right? Because it's sort of, these are like hard balls. They interact very strongly as soon as they hit. Otherwise, they just pass each other. So what is sigma v in this case? This is proportional to v thermal, which is square root of kT by m, or mu, basically, mu. So sigma v, if you plug in the numbers, is equal to right. So if you put in the numbers, it's 1.8 times 10 to the minus 10 centimeter cube per second, T by 100 Kelvin, 1 by 2, mH by mu, 1 by 2, R1 plus R2 by twice 2 angstrom whole squared. Now this is proportional to T to the 1/2. So if your temperature is less than 100 Kelvin, this rate is actually very small compared to this ion neutral rate, which was independent of temperature. I just talked about this ion neutral interaction rate, which was independent of temperature. So those reactions will take place instead of these head-on scattering between neutrals. Okay. Induced dipole interactions are more common. Okay, so this was just like a little idea about these different microscopic collisional interactions. Okay. So now we'll actually start a topic which we'll continue next time, which is statistical mechanics and thermodynamic equilibrium, right? Uh, so interstellar medium or intergalactic medium is far from thermodynamic equilibrium. So what is the definition of thermodynamic equilibrium, right? So if you have molecules in a box, they are in thermodynamic equilibrium if they have had a lot of interactions with each other, like collisions. Through collisions, they have exchanged their energies, and the distribution of velocities has relaxed to the Maxwell-Boltzmann distribution function. Then we are saying that this is a thermodynamically relaxed system. So in thermodynamic, in TD, there is a term called LTE, local thermodynamic equilibrium, local thermodynamic equilibrium. So in LTE, rate of forward reactions, the rate of backward reactions are equal. So LTE, in case of this, particles hitting each other, corresponds to the system relaxing to having a Maxwell-Boltzmann velocity distribution. Similarly, LTE between photons and matter corresponds to photons exchanging energy with matter and relaxing to a black body distribution of frequencies for photons, right? So in LTE, the rate at which the photons are produced by emission, and the rate at which the photons at each energy are reduced by absorption balances. Okay, so 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 but I said that ISM and IGM is far from equilibrium. So why bother about studying local thermal equilibrium if it does not even apply? Even though LTE does not apply in a lot of ISM, the concepts are very, very powerful, and statistical mechanics provides us tools to even like understand non-equilibrium conditions. Okay, and the most important application is something called detailed balance. Detailed balance that allows us. This allows us to relate coefficient of forward and backward reactions. So when I say reaction, I really mean a general process. So you can have, you can have a collision between two particles, and one of the particles can get excited. The reverse of it is the particle getting de-excited, and so right. Let's see, or even easier is this is a recombination. In fact, this is ionization. This is collisional ionization. This is you have an electron and you have a hydrogen atom. Electron hits the hydrogen atom, it ionizes the hydrogen atom, and now you have two electrons. So this is three-body recombination. The forward reaction is three-body recombination. You have H plus and two electrons recombining to forming H and electron, and the reverse is this. So the rate of this forward reaction and the rate of the backward reaction can actually be related to each other, right? So so this is the, so you can relate this sigma, which is a function of energy, of the forward reaction and the sigma of the backward reaction. This is the value of this detailed balance and the ideas of statistical mechanics. So you've already done it. For example, Einstein's A and B are this whole idea of Einstein's coefficients of spontaneous. So, okay, so Einstein looked at the Planck spectrum. Planck spectrum is the thermal spectrum if the photons and matter are in equilibrium. Okay. You can think of, you can think of it in terms of microscopic processes that happens at the level of an individual atom and photon. Processes like spontaneous emission, absorption, and stimulated emission. So the stimulated emission, he sort of guessed it as a fundamental microscopic process by using detail balance and by using the fact that the black body spectrum is a universal spectrum. We'll actually come to that. So that's an example of that. Similarly, there is this Kirchhoff's law. If you remember your radiative transfer, radiative processes in astrophysics course, there the absorption coefficient and the emissivity, right? So this alpha nu and J nu by S nu, there was this kind of a relation. So alpha nu is the absorption coefficient. J nu is emissivity. So, and S nu, which in case of thermal radiator becomes the black body function B nu. So this is absorption. This is emission, right? You are relating absorption and emission. They are inverse processes of each other. So this is also a consequence of detailed balance. Okay, so detailed balance is extremely powerful, and it is used at every place, and it's extremely fundamental idea. Okay, so let's see. So we'll actually first need, we'll need some tools to be able to apply. Okay, just one. Give me 5 minutes after that. So we all started today pretty late, right? So partition function. So partition function is this idea in equilibrium statistical mechanics that we use all the time. This is a function, and it's represented by Z, and this is thermodynamic function, so summation over S, E, E to the, this is exponential. So E to the minus ES by KVT. So this is partition function as applied for a canonical ensemble. So a canonical ensemble is a system with fixed volume, fixed number of particles, and fixed number of particles. In fact, volume need not be fixed. You have fixed number of particles, and it is in contact with the thermal bath. So its temperature is maintained at T. Okay, so this is the partition function. So for a canonical ensemble at temperature T, occupying volume V. Now for dilute gases, which is what we are going to deal with in the ISM, the partition function decouples into two parts. One is the translational partition function, and then there is an internal partition function. Okay. So for example, if you have some X, which is an ion or an atom or a molecule, these will have their internal energy levels, like a hydrogen atom has n equal to 1, n equal to 2, and so on. That corresponds to this part, but they will also have kinetic energy. So your EXI, the energy in internal state I, is equal to P squared by twice mx plus this internal energy, n equal to 1 level or n equal to 2 level, and so on. And P is the linear momentum, of course. So the Z translation is equal to 1 by h cube, this integral d3p d3x, e to the minus p squared by twice mx kbt. Right, so this is the so the partition function is dimensionless, right? It's just a number, a function of temperature. So this is d3p d3x is the phase space volume. This is the distribution function in the phase space volume. 1 by h cube is the this is the quantum of phase space volume. So right, so this whole thing can actually be thought of summation over all possible continuum states, right? This is just like this summation. This corresponds to e to the minus e by kt for these free states. The motion is a free motion, it's not bound. So this gives us, so if you integrate this over, what you get is volume, d3x just integrates to volume by h cube times 4 pi p squared dp times e to the minus p squared by twice mx kbt. If you do this, this is a simple integral to 0 to infinity, of course, and what you get is this is equal to v by h cube times 2 pi mx kt by h cube. Okay. So what you can actually think of it is as the volume which is available to this gas, this dilute gas, times this is like this expression. This is sort of like h, it's proportional to h by lambda. Sorry, this is h by p, right? Cube. This is like a yes, that's fine. So we can actually get rid of this. Right, so this is nothing but the volume of the volume available divided by lambda de Broglie cube. It's proportional to, actually, it's not equal to. So you can actually think of this partition function as not cube. This is the cube, of course. Yeah, you can think of this free space partition function as the phase space volume available divided by the volume of the elementary phase space quantum. Okay, so it's sort of like it's sort of like the number of states available to a free particle. Okay, so this is Z trans, and of course the Z int is nothing but the internal degrees of freedom. That's nothing but summation Gi e to the minus ei by kt, right? This is what we are more used to. That if you have a hydrogen atom, this would be 2n squared e to the minus ei by kt. You sum it over. The partition function is extremely useful, right? You can get all the thermodynamic quantities like specific heat, blah, blah, by taking appropriate derivatives of the partition function, and so on. So the other thing that is you should know is in equilibrium, in LTE, if you have a reaction, a forward reaction and a backward reaction, the partition function on the reactant side is equal to the partition function on the product side. This is very useful. This is very important. This is what will let us be able to relate these forward and backward reaction rates. Okay, I think